Thank you. Hello, everybody. After a break for Thanksgiving, we continue. The next topic in the book is about Parseval frames. But since we talked about kernels, I do the Morse theorem today. And if time remains, I go back to this. It's a very important topic that we need to cover, and many function spaces come out of this result. So we talk about Morse theorem. To prepare for that theorem, let's have an observation first. So let me make it blue. Observation is a lemma about reproducing kernel Hilbert spaces. So lemma, let H be an RKHS on a set omega. And you fix some points, let x1 up to xn be in omega and distinct. Then you can form a matrix with these points and the kernel of the Hilbert space. And here is our matrix. You can see the n by n matrix. K at point xi and xj. And I and j, both of them run from 1 to n. And note that when your points, I mean, x1 up to xn change, the matrix changes too. But for each fix x1 up to xn, you have a matrix. The result is very simple. Then this matrix is positive. Is bigger than or equal to 0. The proof is indeed very simple, but the observation is fundamental for what we want to do later on. Proof. How do we show that something, a matrix is positive? We make that double sum, and we need to show that that double sum is positive. Here is a double sum. Let alpha 1 up to alpha n be complex number, and considering complex is important. You cannot just stay with real numbers. Then the sum over a and j. Here you need to write alpha I beta j and put the conjugate in one of them. Some books put it on alpha I, some on alpha j. It really doesn't matter. To get a nicer formula, I put on alpha I first here, and then k, xi, and xj. The thing I mentioned above, that this matrix is positive, is equivalent to say that this combination is bigger than or equal to 0 for any choice of alpha 1 up to alpha n. But then to show this, just recall the definition of capital K at point x, y, x, z. This is the inner product of the kernel at the function xj, inner product at the kernel at the point xy in the space H. That was the very definition of capital K, which we had a few weeks ago. And as soon as you made this observation, the rest is straightforward, because then, did I write it correctly? Yeah, I mean, I should write kj here and ki over there, because this is kj at point xi. I mean, let me mention here, this is kxj at point xi, which is equal to this one. And now you see why I put the bar on alpha I, even though it really doesn't matter, because now I can take alpha I inside on the second variable and obtain alpha j in the first one, alpha I on the second one. kxi, and this is just the norm of sigma I from 1 to n alpha I k at point xi h squared, and the norm is positive. That's the end of proof. And also the proof has a byproduct for strict positivity. That's the definition of being positive. Sometimes we need to study also being strictly bigger than 0. And strictly bigger than 0 means the matrix is, this sum is strictly bigger than 0, except for the 0 element. And here you see that here you see that this is strictly bigger than 0, except that there is a combination of kxi, if there is xi and alpha I, such that this combination is equal to 0, then you see that your sum, double sum, is equal to 0. Then the double sum that we have above is identically equal to 0. And we do not have a strict positivity. In other words, the kernel function at points for any choice of the points, any finite number of them, should be linearly independent. So I can write it this way. K that we have about is strictly positive if and only if for any distinct collection of the points, the set kx1 up to kxn is independent. We have simply,
Sir,
yeah.
have we defined what is a kernel function?
No, but I say this. I do this for give the motivation for that definition. Now, up to I have started with H, and I say that the kernel has these properties. The kernel of H. Here is the kernel has this property, and then I go backward. Instead of starting with H, I start with a function which satisfies this property. So this part is just observation and motivation. True? So
Yes. So for kernel function is which satisfy the properties of the lemma, right?
Yeah, the proof shows that if H is given, then the reproducing kernel satisfies these properties. First, it's bigger than or equal to 0, and the meaning of bigger than or equal to 0 is precisely from the language of linear algebra.
Yeah,
I mean,
right.
I explicitly gave an n by n matrix. This n by n matrix is always bigger than or equal to 0. This is from linear algebra. And it's not strictly bigger than 0 if there is a dependence relation. We have seen examples of this before. First example is in the Sobolev space. For example, the first one, we had some conditions, and the boundary condition was that f of 0 equal to f of 1 equal to 0. And as you see here, the kernel at point 0 is identical to the 0 function, and the same for kernel at point 1. Each one of these is enough to show that for example, this is just for one point. The set is dependent. Or the other one. So in this case, our reproducing kernel is not strictly positive. We had another example in which, again, in the Sobolev space, I forgot which number was that, but the condition was that f of 0 is equal to f of 1. Not equal to 0, just they are equal. Maybe it was in the exercises I gave. And in this case, this means that the reproducing kernel at point 1, they gave the same value. And therefore, k0, 1 times k0 plus minus 1 times k1 is equal to 0. Another dependence relation. So even in this case, our reproducing kernel is not, is positive. I mean, in this case, of course, we can say that in this example, the capital K is bigger than or equal to 0. Even in this case, we can say that it's bigger than or equal to 0. But it's not strictly bigger because of this relation that we have. But if we go to the Hardy space setting, H equal to H2, our kernel Kz at point W, or usually we write Kw at point Z, is the Cauchy-Gigot kernel 1 minus ZW bar. Is this, I mean, the kernel, is it K? Of course, all the time bigger than or equal to 0, but can we say that K is also strictly bigger than 0? To verify this, we need to answer this question. Is there a collection of points, say W1, W2, and Wn in D, and a collection of scalars in C such that these are distinct, such that alpha 1 kernel at point W1 plus alpha 2 plus alpha n kernel at point Wn equal to 0. We need to answer this. And well, there are several ways to answer this question. One of them is direct. It's doable. I leave it to you. I mean, you have the formula here for KW. Put KW1, KWN, and go ahead. That's direct way. So you do it as an exercise. The second method, if this is the case, for every F in H2, we should have F inner product with alpha 1 KW1 plus alpha n KWN in H2 is equal to 0, because the second component is identically equal to 0. And now if we apply the meaning of KW1, KWN, this is equivalent to say that alpha 1 bar f at point W1 plus alpha n bar f at point Wn equal to 0 for every. And now every here helps us choose specific functions to help us, I mean, very judicial choice of f, such that with that particular f, for example, we can show that alpha 1 is equal to 0. Another f for which we can show that alpha 2 equal to 0, and so on. And you have seen this before. These are the polynomials that we use in approximation. I mean, you can see the f of w. For example, you want to show that alpha 1 is equal to 0. Consider the polynomial, you forget the first term, the second term, w minus w2 up to w minus wn. And you even do not need to normalize it. But if you want to have a normalized polynomial, divide by its value at point W1. And here is the point that you see this assumption is important, distinct. We do not divide by 0. What is the properties of this polynomial? First of all, f at point W2 and W3 and Wn is equal to 0. And second, because of our normalization, f at point W1 is equal to 1. And now for every f, plug f here. If you plug this particular f, you see that alpha 1 bar times 1 plus alpha 2 bar times 0, alpha n bar times 0 is equal to 0. So immediately alpha 1 is equal to 0. And you continue the same procedure to show that alpha 2 is equal to 0 up to, so the same. We can continue and conclude that all the coefficients are 0. And so in this case, the difference between this case, the Hardy space, and the previous cases, the two Sobolev spaces that we saw, it is true that all the time that k is bigger than or equal to 0, but here we can say even it's strictly bigger than 0. So the answer is yes. And with the same reasoning, indeed, I invite you to show that for the Dirichlet space and for the Bergman space, we have the same conclusion. It's strictly bigger than 0. So these were the observation we made about the reproducing kernel of a Hilbert space given. Now we use this to go backward. In other words, we do reverse engineering. Here is the definition. Omega is a set. K, you see, the function k is given now, not the Hilbert space. K defined an omega times omega with values in C is given. It's a function. We say that K is a kernel function if K is bigger than or equal to 0. What does this mean? I repeat the definition we already had before. If for every collection of points, if for every x1 up to xn in the set omega distinct, for every collection of scalars alpha 1 up to alpha n c, the matrix K. The ij element of this matrix is K evaluated at xi, xj. N by n. It's even better to, I have two y's for all. It's better even to add here for all n bigger than or equal to 1. For 1, 2, 3, I mean all dimensions. The matrix is bigger than or equal to 0. So there's a lot of liberty here. The dimension is free, can be dimension 1, 2 for the matrix, 1, 2, 3, any n. And the choice of the points is also arbitrary. I wrote it this way. So I don't need this. Sorry. But if you want to write it more explicitly, you know how to write it. For any collection of the point x1 up to xn, the matrix is strictly positive, which means, I mean, since we came up to here, let me add that this means that the sum alpha alpha j k x x j or x j x I really doesn't matter, is bigger than or equal to 0 for all alpha I. That's the meaning of being positive. Now we can imagine why I gave such a definition. Remember, we had a theorem 2 weeks ago. The theorem was like this: if you have, call 2 RKHs, H1 with kernel K1 and H2 with kernel K2, 2 RKHs, and K1 is equal to K2. The kernels are equal. Then H1 is equal to H2 in the strong sense, which means they are equal as a set, and moreover, they are equal as Hilbert spaces. The Hilbert space, there is an isometry. For every f in H1, the norm of f in H1 is equal to the norm of f in H2. So that's what I mean by a strong equality. So in this case, the spaces are given, and we see that they are uniquely determined by the kernels. That's good. Now we want to go backward or look at this from the exterior. The space is not given, K is given. A function which is a kernel function, which is positive by the definition that we had above. And there are many easy examples of K which satisfy this property. As a very elementary example, I mean, really elementary, any set omega, and consider any function from omega to C, any function, no restriction. And consider, define K of xy by f of x, f of y bar. That's my definition. Can easily show that this K is a kernel function. Indeed, the proof is very simple. What does this mean? What is the sum I from 1 to n, sum j from 1 to n, alpha I, alpha j, k xi xj, and put bar, for example, on this one. This is equal to sum alpha I, alpha j bar, f of xy, f of xj bar. And this is nothing but sum alpha I f of xi mod square, which is positive all the time. So you see, it's not difficult to create a kernel function. This is one of the simplest examples. So parallel to this observation, which says that RKHS are uniquely determined by their reproducing kernel, we may ask, if K is given, is there? It's a question. K given, is there a Hilbert space, H Hilbert space, which is actually a reproducing kernel Hilbert space, such that evaluation function are continuous. Therefore, we have a kernel, and we can talk about little k x, that's the kernel function at point x. So kernel function at point x evaluated at y is our capital K for h, but such that settle, and it's better such that is already up there. Such that EX are continuous, and this is precisely the K which is already given. Or did I write it correctly? No, I should write Y and X. In other words, if K is given, can we have or can we construct a reproducing kernel Hilbert space such that the kernel is precisely the K which is given? And the Morse theorem is indeed the answer to this question, and a very good answer. It means a constructive answer. Not only Morse says that the answer is yes, but only he gives a procedure, which is very natural procedure indeed, to construct the Hilbert space H. So I write the theorem and then give the proof. The proof is long, but a very good proof, because by looking at the proof, you see several techniques, several interesting facts in the proof. So please bear with me, and we go together step by step all the levels of this proof. I write a theorem for reference, and then I give the proof. Let omega be a set, and let K from omega to C be a kernel function. Then it's an existence theorem. So, I mean, all of us as a mathematician, we know that the existence theorem are important. Then there exists an RKHS H of functions on omega such that K, which is given before, is the reproducing kernel, is the reproducing kernel of H. That exists. So that's the message, the main message of this theorem. You start with K, and then you construct H. In several applications, indeed, the construction which is given in the proof is not used. Just the fact that something exists is enough for us. And one of the celebrated examples is the Dobranj-Rovniak space. If you had the chance to listen to Joe Ball talk a few weeks ago, maybe it was last week or 2 weeks ago, he talked about HB spaces. And the way he gave the definition was, he gave the reproducing kernel. In other words, he gave a K, which was positive, and then conclude that there is a functional space for that. And the functional space is precisely the Dobranj-Rovniak space. We will see this in more detail later on. Proof. As I said, it's a long proof, but please bear with me. Let me open another screen to look. We had an observation before, so recall. It was a very simple result, but that result helped us here. If H is an RKHS with kernel K, then the family, or the span of the family, span little kx x on omega, I mean the collection of all reproducing function at points, and then you make finite linear combination with them. This set is large enough in the sense that it's dense in H. That's a result that we saw a few weeks ago, maybe 2 weeks ago. And Morse said that, okay, we want to either find or construct H. We don't have H yet. But what we have, look at the theorem. In the theorem, K is given, capital K. So we can restrict in one argument and let the other argument to be free. And that gives us Kx. In other words, we define Kx at point Y by K of X and Y, or the other way around. I mean, I always. K, Y, X, like that. We define it that way because capital K is given. And if we define it that way and eventually succeed to construct our H, which we do not know yet what it is, this little kx would be, the linear combination would be dense in this space. So let's go backward. We define little kx. We also define W to be a span of these functions. We have all of this. We know that this has to be dense in our eventual space. So we start from here. And here is his procedure. The definition is the first step. The second step, more defined an inner product on W. This is not straightforward. We need to work a little bit on it to show that it's really an inner product. There is no problem. And indeed, the major part of the proof is precisely here. Then we do completion. I mean, every inner product can be completed to give us a Hilbert space. And that Hilbert space, the abstract completion, is not necessarily a family of functions on the set omega, but we need to modify it to obtain a family of functions on omega. We will see how to do that. And that is the space we are looking for. This is our RKHS. So that's the road to follow. So for the time being, W is given. It's a collection of functions on omega, because each kx is a function. When you do linear combination, it still is a function on omega. So the first step, how to define an inner product on W. So we may do naively as follows. We will see what is the problem. May say that let F and G be in W. Therefore, for F, there is alpha 1 up to alpha n, complex number, and there are points x1 up to xn in omega, such that F is alpha 1 little k x1 plus alpha 2, and finally alpha n little k xn. That's true. No problem with that. And the same for G. There is, call it beta 1 up to beta m. And another set of points, y1 up to ym, such that G is equal to beta 1 k at point y1 plus beta m k at point ym. Absolutely no problem up to here. 2, F and G are defined by such combination. And then we proceed to define the inner product. How do we find F and G at point W? I haven't defined it yet, but let's see what we need here. So it's sum from I from 1 up to n, alpha I k x y. And then for G, J from 1 up to m, sum beta j k y g. Okay, I want to define this. Since I want to have an inner product, it has to be linear with respect to the first component and conjugate linear with respect to the second component. So at the end of the day, this should be equal to sum I from 1 to n, j from 1 to n, alpha I, beta j bar, kxy, kyj in W. And what else I want to have? alpha I beta j. I also want the little k to be the reproducing kernel. If I want this to be true, then I have no choice but this inner product to be k of yj xi. We saw this before. If a kernel, it has to be, this inner product has to be equal to this. So I would have a good definition if f and g satisfies this property. I need that. Therefore, I mean, adopt this as my definition. So I define f and g, inner product of f with g in W to be this sum. Forget about the calculation that I did before. I mean, they were just justification for this definition. So I use this as my definition. And you should immediately tell me what's the problem. As definition, I mean, I have f, I have g, so I define as this sum. But there is a problem here. Chat.
Whether it is well defined?
Yes, in other words, well defined, this means that f is represented by this combination. It's not unique. It might have another representation. So I write behind this with another color. So it might be also equal to alpha 1 prime, kx1 prime, and alpha, say, p prime, not necessarily even the same number of points, kxp prime. And the same for g. G might be beta 1 ky1 prime up to beta, say, q prime, yq prime. For both, another set of scalars, another set of points. So if I choose the red one, I see this also has to be equal, and I don't know this. I have to verify. Is it also equal to sum from 1 up to p, j from 1 up to q, alpha I prime, beta j prime bar, k at point yj prime, xi prime? That's the big question. If this is not the case, my definition is not a good definition. It doesn't make sense. And that's, I can tell it's pretty much the heart of proof is precisely here, this verification, that W is well defined, the rest is automatic. How, why is this well defined? So go back to what we had for f. F on one hand is equal to alpha 1 kx1 up to alpha n kxn. And on the other hand, for another set of scalars and points. But whatever is the representation, the value of f at any point is well defined. So for any y in the set omega, f at point y is this function at point y or this function at point y. They have to be equal. And the evaluation of that function at point y is alpha 1 ky at point x1 plus alpha n capital K at y at point x1. This is the evaluation of this function at point y and the evaluation of the other at point y. This is an important identity. Very important identity. Alpha 1 prime k y x 1 prime alpha p prime capital K y x n prime. That's the key to success, this identity. So remember this. It is true that you may have many different representations, like the one here or the one there. But when you evaluate at points, different points of omega, you should get the same value. That is why I have this combination equal to this combination. And now I can show.
The last index should be P rather than N.
For the first one is N, for the second is P, because we don't have necessarily the same number of points in the second representation.
Yes, so shouldn't it be XP prime?
Oh, yes, thank you. Here, P prime. Thank you. And now, using this identity, which I wrote for F, we have the same identity for G. I can show this identity. The answer is yes. And let's see how we do this. It's not that difficult now. Let's start with the first one, the sum. I from 1 up to m, j from 1 up to m. I have to be very careful here not to mix the different indexes that we have. K, y, j, x, I. That's the combination I have here as my initial definition with the representation I chose, but I should show that for any other representation, I obtain the same number. We have identity here. And to do this, I keep the summation over j, so beta j bar, and keep this the summation over I inside. You see, the summation is over I, and the purple identity here with y replaced by yj, I can go from this sum to the second sum. So that is why here I can say sum j from 1 up to m beta j bar, and replace this sum by sum I from 1 up to p alpha I prime k here x I prime at the same point, and the point here is yj. Point repeats. So it's identity above that we have for point y. I write it for point yj and put it there. So that's one step. Now I change the order of summation. I keep I at the beginning, and then j inside, beta j bar k y j x I prime, and do the same thing, knowing that since k is positive, if you consider 2 by 2 matrices with 2 points, you see that when I change the order here, I have to consider the complex conjugate. In other words, this is equal to the same thing here, the same thing here, and here is k x I prime y j bar. If you change the order of the arguments, you need to put a bar over there. And now take the bar outside over the bracket. And what can you say about beta j k xi prime yj. There is a bar here. And you see now our argument, which is fixed, is this one. And the summation is respect to beta j. And this is a representation for the second function. So it's the evaluation of the second function g at point xi prime as this one when we did this move. When we did this move, this was the evaluation of the function, well, f at point yj. Just keep in mind. And this is without the bar. This is the evaluation of the function g at point xi prime. So if you use the second representation for g, this is sum, was it n or m? J is from 1 to n. The second representation, j is from 1 to q, beta j prime, k, xi prime, yj prime. And there is a bar here. I made a mistake here when I took this sum out. I continued to write n, but it's p. So the sum a from 1 up to p alpha I prime. But now I put bar back inside again, almost finished. This is q, beta j prime bar, and k bar, which I write it as yj prime, xi prime, and sum I from 1 to p, sum j from 1 to q, alpha I prime, beta j prime bar, k y j prime xi. This is precisely what I wanted here. If you compare the first and the last, this is precisely what I want here. And that is why my definition is a good definition. Doesn't matter which representation you use, either for f or for g. At the end of the day, when you do this summation, you obtain the same number. So f inner product with g in w is well defined. Point. This part, as I said, is the most important part of the proof of Morse theorem. Before the break, let's make one observation, one further observation out of this fact that it doesn't depend on the which representation we use for f or g. Given f in w, for g, choose k, y. This is an element of w too. With the definition we gave, and you see why we gave this definition, what is the inner product of f and g, or better to say, the inner product of f and k, y in w? Well, the definition is here. This is the sum, except that the second sum, j from 1 to m, there is just one in the j is from 1 to 1. I mean, we can use any representation that we like. I mean, it's already ky by itself is a representation. And ky is equal to 1 times ky. It's funny, but that's the way it is. We show that it's well defined. So it's sum I from 1 up to n. That's a representation for f. J from 1 to 1, alpha I, beta j bar, but beta j is just one of them, just beta 1, k at point yj xi. So it's, I simplify I from 1 to n, alpha I, beta 1 is 1, k1, ky1 is ky, and xi. And you have seen this combination before. You have seen this combination before. This is precisely the evaluation of f at point y. So that, in other words, the inner product is defined, and it's well defined in such a way that for any f in W and for any point in the set omega, f evaluated at point y is equal to inner product of f and kw and ky in W. And this shouldn't be a surprise. We want this to happen. This is our goal at the end of the day. It's not fully realized yet because, well, some properties have to be checked yet. That this is an inner product, it's not completely verified yet. That's one thing. And more important than that, W is not complete. So we need to do more work. And well, we continue after the break for the rest. It's 58, 10-minute breaks, and we come back.